Good morning, students. So in this unit we have divided into two sections. So this is what we planned. So one is for one dimension, another one is for 3 dimension. So we solved so many models for one dimensional problems. Especially we solved starting the wave equation to obtain wave function and energy eigenvalue for infinite quantum well. So this is what we started in the unit. Then after that we solved the same model for finite quantum well, then potential barrier. And this is about the 3-dimensional models. And in fact the reality is 3-dimensional models. We have approximated and we calculated the required things, which is the wave function and energy eigenvalue for 1-dimensional model, and we are going to apply the same model into 3-dimension one. And for 3-dimension one we will have to use 3 coordinates. For 1-dimension one we will have to use only 1 coordinate. The solution will be very easy when we solve a 1-dimensional problem. This is one direction, 1 coordinate. So solution will be very easy. Whenever we are going to use 3-dimension, we will have to use 3 coordinates. So it's very difficult to solve 3 coordinate system. So the idea is we are going to separate all the 3 coordinates using separation of variables. So that's a technique that we are going to use. The separation of variable techniques we have already used in the unit 1 to derive Schrodinger's time dependent equation and independent equation. We used that technique, separation of variable. There we use the wave function psi, which depends on position coordinate and time coordinate. We have separated, and we could obtain the Schrodinger equation in terms of time independent equation. Can you remember? So similarly here also we are going to use 3 coordinates. 3 coordinates, it can be either Cartesian coordinates like x, y, z, or even it can be, we are going to consider a system as a sphere. Then we will have to use polar coordinates r, theta, phi. So we have x, y, z, we can separate into 3 coordinates, and polar coordinates r, theta, phi, spherical polar, that also we can divide into r, theta, phi. So using separation of variables techniques. Now r, theta, phi, r stands for radial part, theta and phi both stand for angular parts, and there theta is nothing but the polar angle, phi is nothing but azimuthal angle. So that technique we are going to use. And some of the existing problems, for example, just take diatomic molecules, some model, for example even atom itself, that can be solved using spherical polar coordinates, the hydrogen atom problem. So they are all very simplest things. So we are going to use in this class, we are going to have 2 sessions. One session stands for the techniques that we are going to follow, that is using the separation of variable. Then another one is we are going to use 2 body problems. So these 2 concepts will be used for our next session. So next session we are going to learn hydrogen atom and rigid rotator. So for that we need these techniques. So that's the idea. Okay, we will start the problem. So particle moving in a spherically symmetric potential. So it's given as spherically symmetric potential. The potential is spherically symmetric. If it is spherically symmetric, it has to obey this rule: V of r vector equal to V of r. Very, very important concept. Okay, the potential is spherically symmetric. It implies that V of r vector equals V of r. So it implies that there is no direction on the right hand side. Correct? So we have a vector quantity, direction and magnitude. So direction is discarded. So we are not going to use direction. Only magnitude alone will be there. That means the motion of the particle depends only on the magnitude from the fixed point. Suppose if you consider a sphere, the potential is everywhere, it's uniform, spherical. We are going to consider only the magnitude, not the direction. So the first point says that spherically symmetric potential, it means the motion of the particle depends only on the magnitude of the distance from the fixed point. Of course, the potential depends only on the position, not on the direction. So this equation says, for such a system, the time independent Schrodinger wave equation is given by this. So here, for spherically symmetric potential, so we will have to consider V of r vector equal to V of r. So first one is about the potential, the problem inside the potential. And next session will be problem without the potential, two-body problem. So that's we are going to consider. So these techniques will be used for the next problems. So that's why we are studying now. So this is Schrodinger time independent wave equation. We know already, we have already studied. And the potential is spherically symmetric. Now we are going to use spherical polar coordinates r, theta, phi. So r is the radial part, theta is the polar angle, and phi is the azimuthal angle. Okay, you should remember. And the limits will be, for r it lies between 0 and infinity. So it goes from 0 to infinity, you should remember. And theta 0 to pi, phi 0 to 2 pi. You should remember all the three coordinates. Okay, one is 0 to infinity. 0 to infinity in the sense 0 from 0 the origin to the maximum radius. Suppose the radius is capital R, then infinity is nothing but your capital R. Okay, so r lies between 0 and infinity, theta lies between 0 and pi, and phi lies between 0 and 2 pi. You should remember. So this Cartesian coordinate Schrodinger wave equation can be written in terms of polar coordinates exactly like this. Okay, polar coordinates. So this equation, okay, this is in terms of polar coordinates. Now it depends on r, theta, phi. It just psi depends on r, theta, phi. Here also psi depends on r, theta, phi. Okay, everywhere psi depends on r, theta, phi. Psi is the function of r, theta, phi. So as I said, we are going to separate the equation. R separately, theta separately, phi separately. That is the idea. Okay, because we have three coordinates. Is it applicable only for three coordinates? No. Is it applicable for number of coordinates? 2, 3, 4, anything. We can use this technique, separation of variables, to separate the coordinates. So the solution. So this can be separated. The solution can be written as the product of radial part and angular parts. The solution can be written as r of r, theta of theta, capital theta of small theta, capital phi 1 of small phi. So remember this one. So these are the three variables now. Now you are going to substitute in that equation. So when you are going to substitute for psi, that will, instead of psi you are going to substitute r, theta, phi. Is it okay? So in the previous equation psi is here. So instead of psi you are going to substitute r, theta, phi. So again psi instead of psi r, theta, phi. Instead of psi r, theta, phi. Okay. So like that we are going to substitute. Now you just multiply by this factor r square sin square theta divided by r, theta, phi. Our aim is to separate r, theta, phi and get the solution. So that is the idea. So now we are going to multiply this. So when you are going to multiply, this will give you this r squared, correct? R squared sin square theta. Now look at this equation. It depends only on r, and theta and phi are constants. So you pull it out. So it depends only on small r. Okay, radial. So we can write this as dr by dr. Okay, partial dr by dr. Is it okay? What I am saying? So this r squared is here. This d by dr is here. And of course your r squared sin square theta divided by r, theta, phi. The theta phi will cancel. You will get only r squared will get cancelled. You will get only 1 by r. Is it okay? In the next equation we are going to see 1 by r. Is it okay? Okay. Now look at the next equation. The same factor you are going to multiply. Now here r is constant because depends only on theta. So r and phi both are constant. You pull it out. Okay, you can pull it out. R, phi. Here it depends only on phi. So r and theta you can pull it out. The next one. So r and theta. It depends only on phi. So we have written phi. And of course the last factor, let it be like this. Let it be like this. And of course this, all those things are constant, r, theta, phi. So this one and this one will get cancelled. Is it clear? Okay. Very simple one. So as I said, we have the first one sin square theta, r square will get cancelled, theta phi will get cancelled. You will have 1 by r. So sin square theta by r, d by dr. Now look at the first equation. It depends first expression in the equation, you have it dependent on r, it depends on theta. Okay, look at the next one. As we have done, we have simplified all those things, we have straight all the similar terms, and we have obtained this one. It depends only on theta. So we are going to separate slowly, and it depends on r comma theta. And look at the third one, third expression. So third expression is this one. You strike all the similar terms, you will get d squared phi by d phi squared alone. See, I have pulled out 1 by phi. Of course, you have 1 by pi. R theta will cancel. You have 1 by pi. So this will give you that side. I'm going to bring it to right hand side. That will give you minus 1 by pi d squared phi by d pi squared. It depends only on phi. We have separated now phi out. Correct? So right hand side it depends r comma theta, whereas left hand side it depends r comma theta. Right hand side depends only on phi. So we have separated. If it is so, we have already studied, then it must be equal to some constant. So this is r comma theta, that depends on only on phi, like p1 b1 equal to p2 v2 equal to some constant, so something like that. So we can equate to some constant. So we have equate to some constant. That is constant is nothing but your m square, where m is the magnetic quantum number. M depends on azimuthal angle. Okay, phi. So that's why magnetic quantum number exists. It comes here. So is it okay? So now just remember this equation. You have separated one equation. Okay, you will stop here. Then we'll go for the next one, the remaining things. We'll try to again separate two variables r and theta. You have separated phi. We'll stop here. Okay. Then now this will be your r and theta, as I said. So depends on theta, depends and r comma theta. Correct? Which is equal to some constant. This is nothing but m squared. Now you just divide both sides by sine squared theta. Just divide by sine squared theta. So this equation becomes like this. So you have sine squared theta divided by sine squared theta, this factor, same factor, and divide by sine squared theta, divide by sine squared theta. So m squared divided by sine squared theta, that side also, right hand side also. Now this one will get cancelled, and we have 1 by r, d by dr, r squared dr by dr. Look at this one, it depends only on r. So we have used the correct technique. We have depends only on r. What if this is a third term? You just strike these one, sine square theta, it depends again only on r. You just pull third term to this side. What is second term? Second term, you just look at the second term, it depends only on theta. So you bring it to right hand side. Is it okay? Very simple. So you have brought this term to right hand side, and already we have that term. So that is nothing but your plus m square divided by sine square theta. So right hand side depends only on r, left hand side depends only on r, right hand side depends only on theta. So slowly we are building up. So this must be equated to some constant as usual. So this equation is equal to some constant, which is nothing but your lambda. So this equal to lambda, and this factor also must be equal to lambda. Okay. So if you equate to this one, so this will become. So this will become equal to lambda. So I can bring this lambda, or I can take this term to that side, and I can rearrange. We will get this lambda minus m square. I multiply throughout by minus sign. So you will get here also you will minus sign, minus lambda. You bring minus lambda to left hand side. You will get lambda minus m square divided by sine square theta of theta, which is equal to 0. Is it okay? So this term depends only on theta. We have separated. Radial part, it depends only on r. It depends only on r, which is equal to lambda. Can you remember? So lambda we have brought it here and multiply throughout by r square, divide by r square, that will give you this one, this equation. Okay. So like this, we have separated the spherical polar coordinates of a system, of a sphere, of a spherical system into three separated equations. One depends on theta, then another equation depends on phi, and depends on r. So this is the idea. Okay. So separation of variable technique is the best technique, where we can separate all the coordinates to simplify the problem. So now we can solve it. We can solve this problem, we can solve this equation, we can solve the phi equation. It's very simple. First we will solve phi equation, which we have already discussed earlier. Your phi will be a e power, the solution of. So this equation we already got. Can you remember? This solution is 2.208 for the phi dependent second order differential equation. And the solution of this one will be a e power plus or minus I m phi. Solution of this. Okay. And so the important thing is, and phi equals 0. Phi equals 0, as well phi equal to 2 pi, we have a single value, because this is just like a rotation. Suppose the point is here, you have a value, then for 2 pi again same value we can obtain. So we are going to simplify into this expression like a e power I m pi can be written as phi plus 2 pi, because they will have same value. So phi plus 2 pi, you separate this. So this will give you a e power plus or minus I m pi plus or minus I m 2 pi. E power plus or minus I 2 pi can be written as cos 2 pi m plus or minus I sin 2 pi m, correct? Plus or minus. So there's a mistake here, plus or minus. And if you write m equal to 0 here, you just substitute m equal to 0. Cos 0 is 1, sin 0 is 0. So you will get 1. So 1 equals e power I plus or minus I m 2 pi, that m goes from 0, 1, 2. So something like that. So it's a quantum number. So especially this is called a magnetic quantum number. Is it okay? So now the normalization condition. Of course we know normalization condition that goes from minus infinity to plus infinity, we know. But here phi, limit for phi will be 0 to 2 pi. So that's why we return 0 to 2 pi. Normalization condition we know already, this one, which is equal to 1. So you square of the wave function, that will give you like this, equal to 1. So mod a square 2 pi equal to 1. So a will be 1 by 2 pi. 0 to 2 pi d phi, you just integrate, that will give you phi. 0, substitute 0 to 2 pi, so you will get 2 pi. So a equal to 1 by root 2 pi. So your complete wave function, normalized wave function will be phi equals 1 by root 2 pi e power I m pi, where m equals 0 plus or minus 1 comma 2. Okay. So we have solved now phi. We have got the solution for phi differential equation. Now we will go for the second one, theta. Okay. The last one will be r. Is it okay? So to solve theta equation, new variable we are going to introduce z equal to cos theta. We are going to introduce. So this is the technique that we are going to follow. So differentiating, that will give you dz equal to minus sin theta d theta. Okay, you are going to differentiate this equation, you will get this. And I can write this equation exactly like this. That is, I am going to bring d theta down this side, dz to this side. So that will give you 1 by d theta, correct? Minus sin theta 1 by dz. So I am going to use d on both sides. So that will give me d by d theta, which is equal to minus sin theta d by dz. Is it okay? Is it okay? dz to this side, d theta to this side, and I can write d by d theta on both sides. Okay, to equal the both the expressions, left hand side, right hand side. Is it okay? Now we know that sin theta can be written as 1 minus cos square theta. Okay, sin square plus cos square equals 1. We know already. So cos theta equals z. So 1 minus cos square theta will be 1 minus z square. So minus 1 minus z square to the power 1 by 2 d by dz. We are going to use this one. Okay, wait for this equation. We know already the theta dependent equation is given by 2.211. We know already this. You substitute here 1 by sin theta. Instead of sin theta you can write 1 minus z whole square to the power 1 by 2. 1 minus cos square theta to the power 1 by 2, correct? Multiplied by, the next one will be d by d theta. D by d theta is nothing but this factor. So with a minus sign, 1 minus z whole square, z square to the power 1 by 2 d by dz. Next factor is sin theta. Your sin theta, correct? Sin theta is 1 minus z square to the power 1 by 2. Again d by d theta. D by d theta is minus, so minus this factor. Is it okay? Plus your lambda is here, minus m square divided by sin square theta is 1 minus z square. So we have filled up. Now this term, this term will go off, will get cancelled. Minus and minus, that will give you plus. So this comes plus. You have d by dz. 1 minus z square. 1 minus z square will give you to the power 1 by 2, that will give you 1. So 1 minus z square alone. So d theta by dz. Now here theta depends on z because we have converted it to z everything. Okay. So lambda minus m square divided by 1 minus z square theta, which depends on z. So can you remember this equation? This is your associated Legendre equation, which we studied in mathematical physics earlier. So this is exactly resembles with associated Legendre differential equation. And the solution is nothing but Legendre polynomial. So we can go with the Legendre polynomial. For theta dependent relation, for any spherical system, we are going to have the solutions as Legendre polynomials. So that's the idea. Okay. So the poles are nothing but z equal to plus or minus 1. It means that minus 1 to plus 1. The limits will be plus minus 1 to plus 1. And of course lambda is connected with orbital quantum number. Like phi and m, we said m is connected with magnetic quantum number, where lambda is connected with orbital quantum number, and L goes from 0, 1, 2, and m goes from 0 plus or minus L. It's a very important thing, plus or minus L. The solution, as I said just now, which is nothing but Legendre polynomial, which is nothing but PL of Z. For m equal to 0, the associated Legendre polynomial is given by this factor, PL to the power mod m of Z. Okay, for other things. So the complete solution is given by this with a normalization constant. So normalization constant depends on Lm, and this will be your Legendre polynomial. Product of these two will give you the complete solution theta dependent. So we have finished now phi and theta. Okay, we have finished phi and theta. But however, we will have to calculate the normalization constant. Correct? For that, what we are going to use again normalization procedure. So as I said, minus 1 to plus n. Correct? Just now I said. So this term can be written as a conjugate, which is equal to 1. The value of this one will be this. So your normalization constant is given by this factor, again which you have already studied in mathematical physics. Okay, this one. So this is a normalization constant. Okay, so normalization constant multiplied by this factor. So we have already done. That will give you complete solution. So NLM we have already found out. Correct? Here you have NLM multiplied by this, which will give you the complete solution. This is nothing but PLM cos theta. Okay. So this is the complete solution for theta dependent equation. Okay, for any spherical potential problem. Okay, and I have introduced now epsilon, and this factor says that when epsilon equal to 1, m is less than or equal to 0, and epsilon equal to minus 1 to the power m when m is greater than 0. So depending on the m value, we will get epsilon as negative or positive. Okay, it is like that. Okay, is it okay? Now we have already studied in this section theta and phi. So phi we derive the solution for phi. Second one theta. Put together we call this as spherical harmonics. That is polar angle. Another one is azimuthal angle. Okay, this is angular parts of the complete wave function. That will give you the spherical polar coordinates, which is denoted by this symbol YLM, theta comma phi. So spherical harmonics. The solution of angular part of the equation is called spherical harmonics and independent of E and VR. Okay, and this is radial part. So combining 2.224. So this one combining, okay, and 2.216 is the phi part. So put together that will give you complete solution for spherical harmonics. So this is your radial part and this is your phi part. Phi solution. Can you remember this phi solution? So product of these two will give you the spherical harmonics put together. Okay, where L goes from this factor and M goes from this condition. Is it okay? You have 2, here also we have root 2 pi, so that will give you 4 pi. Okay? Other things are all same. The presence of the factor e power im5 makes the spherical harmonics complex sometimes. In general, it will be very easy to work with the real form. So, because this factor is the e power im5, so we will get a complex value. Correct? E to the power im5. We will get the solution as a complex value sometimes. Okay? But it is always better to work with a real factor. Okay? So now we'll go for the radial equation. Is it okay? So first we solve for the phi dependent, and second one is theta dependent, and next one is r dependent, radial part. So this is your radial part, which we have taken from 2.212. Okay. Now here you just substitute r of r equal to chi of r divided by r. You just substitute and just try. That will be your assignment. Okay. You just try. You will get this expression. Okay. So that will be your assignment. Plus 2m by h bar squared e minus v of r. You look at this one. You have lambda by r squared. Lambda by r squared. Here 2m by h bar squared. We have taken common out 2m by h bar squared. So you have to multiply by h bar squared by 2m to bring a 2 inside the bracket. Is it clear what I am saying? Come on. See, 2m by h bar squared is here alone. There is no 2m by h bar squared. But we have put it in the bracket here. A common bracket. We have taken as 2m by h bar squared common. So for that we have to multiply by h bar squared divided by 2m. Is it okay? This has the form of a one-dimensional Schrodinger equation of a particle of mass m moving in the direction of r in the field of effective potential. Why we are saying effective potential? Because we have subtracted one term. This is ordinary potential, E minus V of r. Suppose if it is not here, L equal to 0, it exactly resembles with our one-dimensional Schrodinger wave equation. It is easy to solve. R can be easily can be obtained. But here we have added some factor here. So that's why put together we call this as effective potential. E minus of VR minus of this factor. So this is called the effective potential. These two terms are called the effective potential. Okay. So now we will see what is the meaning of effective potential here. So V effective is nothing but V of R plus this factor. Okay. You pull minus out. So that will be V of R plus. So this is your effective potential. And this effective potential is nothing but a repulsive force, repulsive one. Effective potential is nothing but repulsive force. So how to get this repulsive force? We know already F equal to minus del V. Negative gradient of potential is nothing but force. Okay. You just substitute here. You have V is here. This is your V. Additional potential. Okay. You just substitute here. So differentiate this with respect to R. R squared, this is in the denominator. You just make it into numerator. So r to the power minus 2. You just differentiate. That will give you minus 2 r to the power minus 3. So minus 2 divided by r cube. That 2 will get cancelled. You have r cube. L into n plus 1 h bar square divided by m r cube. Is it okay? That minus and this minus will get cancelled. We will have plus term. Is it okay? So this is nothing but your force. This is nothing but your potential. This force is nothing but your centrifugal force. Centripetal force is attractive force. Centrifugal force is repulsive force. That's why we have repulsive one. So this term is denoted as a centrifugal force, which is nothing but mr omega square. Okay, mr omega square. We will write mr omega square. Now how we are going to write this term into force, and this term is a centrifugal force, and this is connected with L, capital L. We are going to say. Okay, so mr omega squared, which is equal to, I am going to multiply on both sides by divide by mr cube divided by mr cube. So these two terms I can write this as mr squared omega whole squared. Correct? You have m squared r to the power 4. Correct? R to the power 4 and m squared. So we can write this as whole squared. Is it okay? Divided by mr cube. And mr squared omega is nothing but your L. So L squared divided by mr cube. Okay, L squared divided by mr cube. Your L squared is nothing but L into L plus 1 h bar squared. So there's a connection between these two. This is orbital quantum. Okay, orbital quantum number. So this is orbital angular momentum. This is orbital quantum number. So there it's connected. So this form of the centrifugal force and the force corresponding to additional potential is given by this expression. So that's the idea. So as the quantum number L is associated with the orbital angular momentum is called orbital angular momentum quantum number. Okay, is it okay? So now we have separated this part and r part, theta part and phi part.